Hello, welcome to the RMG workshop section on the RMG database and parameter estimation. I'm Matt Johnson. So we're going to talk about the RMG database, what's inside of it, how RMG estimates parameters, and in general, how to understand sort of the internals of how we estimate parameters and how we look at parameters in kinetic models. So looking at a chemical kinetic model, essentially we have a set of reactions and parameters that determine the rates for these reactions. And so if you have this reaction A to B, to properly define this reaction, you have to know both the forward rate and the reverse rate. However, we have a really nice relationship from thermodynamics between the forward and reverse rate and the Gibbs energy of reaction. In general, we calculate the reverse rate as a function of the forward rate and the Gibbs energy of reaction because thermodynamic properties are much easier to estimate than rates, both in terms of calculations and in terms of in general estimates. You also get very nice cancellations of errors with thermodynamic properties that you don't get with kinetics. There also tend to be more reactions than species, which means you're estimating less properties. And additionally, oftentimes thermodynamic consistency in a kinetic model is far more important than in individual rates. And this implies that we have two separate main problems of interest, which are estimate the heat of the Gibbs energy of reaction and estimate the forward rate coefficient. So looking at the Gibbs energy of reaction, so we have this relationship between the enthalpy and entropy of reaction, the Gibbs energy of reaction. And then we can deconstruct the enthalpy and entropies of reaction into the individual enthalpies and entropies of the individual species involved in the reaction. If we assume ideal gas behavior, which we generally do for the first sort of step in terms of estimating this stuff, and then sort of add corrections after that, we can relate these enthalpy and entropies of these individual species formation to their values at 298 Kelvin and also the heat capacities at constant pressure. And in general, what this lets us do is this lets us get the Gibbs energy of reaction in terms of those three properties for each species. Now, how do we get those particular properties? So the best way to compute these is always going to be experiments, but experiments take a long time to do and are very time consuming and a lot of work. And usually if you have a 400 species in your kinetic model, you don't really want to design and run 400 different experiments just to see what the kinetic model looks like. So the next best way is quantum chemistry calculations, which in general, if you don't need really high accuracy, are a whole lot faster than experiments. But these still take a whole lot of time to run, especially, I mean, it may take a good calculation at a reasonably sized molecule might take a day to run. But during an RMG run, we don't really have time and don't really want to run quantum calculations for every single species that we have, usually. And we need fast ways to do that. So an RMG has a couple different fast ways to do that. So the first main one is group additivity based on Benson's method. So the idea is in general that thermochemical properties are highly linear. The enthalpy of a species can, to some approximation, be decomposed into the enthalpies of the individual atoms separated and the bond association energies associated with forming all of the bonds. And what this lets us do is this lets us define those thermodynamic properties as a sum of contributions from individual atoms with a given local structure and add them up to get the enthalpy of the whole molecule. In a certain sense, you're averaging the bond association energies into these individual correct contributions. In here, as you can see here, we identify a particular atom that each of these corrections is associated with in this molecule of propane. And So we have one for the carbon on the end, one for the carbon in the middle, one for the hydrogen on the end, and one for the hydrogen in the middle. Now, in general, it doesn't actually look like this because the hydrogens are the value for these groups are actually linearly dependent on the value for these, because you'll never have this group without having hydrogens associated with it. So in general, hydrogens won't have values associated with them. And this occurs for a couple special cases for other atoms. But the idea holds. So in order to determine these contributions, we estimate them by descending a thermotree in our database to the most specific node, where we start with at least some of sort of less specific sort of descriptions of the atom, such as just a carbon atom, and descend to more specific and more specific representations. When you'll go all the way down, and then at the bottom, when it hits the most specific node that matches it, that node will either have data, a reference to another node, or none. Now that reference to another node may have data, or it may have another reference, and that none will simply just reference it up to the next most general node up the tree. These contributions are usually either from literature or derived or fitted to simple molecules. Now, so far what we've talked about doesn't really deal with radicals in particular. And for radicals, we use a similar tree of hydrogen bond increment corrections, which essentially estimate the energy difference caused by removing a specific hydrogen atom from the molecule, leaving behind a radical. And you would apply, if you had a dirad, you would apply this two times within the molecule. And these corrections are based on semi-empirical calculations, which is why GAV works so much better on stable species than it does on radicals. So now we'll take a look at the main thermotree. So this is what the main thermotree for RMG looks like. And what you should note here is that the atom of interest is designated with a star. And this becomes important as you look at these sort of larger groups that have a star that sort of denotes the atom the correction is associated with. As you'll note here, this one has data associated with it, whereas this one here has a reference to another node. And if we were to dig a little bit farther, we'd find ones with none there. But if we look at the bottom, we can see the tree structure, which sort of sets all of these nodes in the hierarchy, which is quite large, as you can see here. But it sort of looks at sort of the general any atom, the carbon case, and then these special cases of the carbon atom, and more special cases. As you can see here, we have a lot of these nitrogen groups here. Not all of them are filled in, as you'll find, but many of them are. So now we'll take a little bit aside and talk about adsorbates on catalysts, which is similar but kind of a little bit slightly different. And broadly, it looks a lot like sort of a normal thermocalculation. And indeed, in a lot of cases, it will start just pulling information from the gas phase database or from estimating the species from thermochemistry to get the energetics for the gas phase species. And then it will add an absorption correction based on an absorption tree, much similar to the thermotree I just showed you. And this will give you sort of an estimate of the value on platinum 111, which is what all of the catalyst absorption is sort of based on. You can also pull information from an adsorbate database, and then these adsorbates, their energetics are corrected based on the delta of the binding energy for the actual metal that may not be platinum 111 to give you the thermo for any arbitrary absorbing. So the other main method that RMG has for estimating thermochemistry is a neural network method. So what's special about neural networks is that unlike most standard regression techniques, they aren't as, in general, sensitive to your choice of inputs called features, as long as you choose enough of them. And neural networks essentially are nonlinear models that are composed of multiple layers of neurons that each try to refine their inputs into better features until they can predict the output properly. The general sort of equation for one neuron, from one neuron layer to the next, is here, where WK is matrix transforming the results from the last layer, and this bias term BK, and then some nonlinear activation to give you the next layer. So what we use is a graph convolutional network, and this is a fancy way of saying that a neural network structure that treats locally identical structures within the molecule the same way, regardless of their global position. And this, in general, reduces the number of weights, and it tends to also improve results for the model. Once you have this network, it can be trained by stochastic gradient descent on a set of training models, and this leaves you with a set of neural net weights, which are essentially these sort of values, these parameters associated with the neural network. And from these weights, predictions and uncertainties can be estimated within RMG. In general, the neural network estimator works well on unfused polycyclics and fused polycyclics, and then it also works quite well on nitrogen. But for other species, group additivity is usually much better predictor right now, at least. So now we'll talk about estimating the forward rate coefficients. So once again, the best way to get these is from experiment. And the next best way is from quantum chemistry calculations. However, transition state theory calculations are much more tricky than thermal calculations, and there's a lot more nuance to them, and so they're a little bit more time consuming to get. In terms of fast ways, there's some additional complications with rates. Rate coefficients have a nonlinear relationship with the molecular structure of the reactants, which unlike thermochemistry. And there's also a lot more special cases than there is in thermochemistry estimation. And another sort of particular thing is that it's very important that you want to get the exact answer if it's present in the database. In thermochemistry, it often doesn't matter as much because you get good cancellation of errors between the two estimates. So broadly, the idea with rate trees is very similar to that of thermo trees. We structure our rate information within these isomorphic trees, or trees where each structure matches the structure above it, is a substructure of the structure above it. And then we use the distance within these trees to determine what kinetic parameters are best for what reactions. So what's a rate family? So a rate family is a recipe up here with an associated set of trees. And each of these trees describes an independent or semi-independent section of the reactant's molecular structure. And each node structure in the tree is subgraph isomorphic, or it matches, each one is a subgraph of the molecule of the functional group structure above it. So within the rate tree, there's a couple different kinds of information. So the first is a rate rule, which is simply set at a fixed location within the tree. And the second is a training reaction. So at the beginning, whenever you load the RMG database, the set of training reactions is descended down the tree to find the most specific node. And then it's placed there in the tree as a rate rule. Note that we're talking about a sort of a two-dimensional descent here, because these sort of separate structures. So it's going to descend down each of these trees separately, and its sort of location is kind of a coordinate in this tree and a coordinate in this tree. So maybe at this and at this. Once we've descended all of these reactions down the tree and we have our main rate rules, it's often still very useful to have upper level rate rules that might otherwise be empty. And so we average rate rules up the tree. And so after all the trees are full, we look at all the distance 1 children, going recursively up the tree. So at this node, at the coordinates of this node and this node, we might look at the 1 children from that, which would be this structure, along with all of these. Whereas we also would look for averaging at stuff that is this matched with these nodes, and so on up the tree recursively. Once the tree is full, we estimate kinetics by descending a arbitrary reaction of interest down the trees. If there's no information at the coordinates where it lands, the closest kinetics information calculated by the 2 norm is averaged to give an estimate, logarithmically, of course. This 2 norm is in this tree space, and in a certain sense, it only considers moving up the tree. So if you would need to move up 1 in this direction, up 1 in this direction, you would have root 2. That would be root 2 Euclidean distance. Other kind of main things to know. So bimolecular trees usually have 2 trees, 1 for each of the reactants, whereas unimolecular trees usually have 3 trees, which is a little bit counterintuitive. But in general, when you're dealing with a unimolecular tree, you have one end group that is reacting with another end group on the molecule, and then you have the atoms that are in between those 2 end groups, which forms the backbone. And those three sections are looked at in most of the unimolecular trees. So let's look at an example rate tree. So here's the rate tree for intra-H migration, or intramolecular hydrogen migration. And essentially, sort of the big, most important thing up top is this recipe, which is essentially what tells RMG what what bonds to break and what bonds to form, where to put radicals on when this reaction happens. As you can see here, there are three primary labels that are associated with this reaction: star 1, star 2, and star 3. So broadly, this tree is unimolecular, so it's broken up into 3 different main trees. XH out, which is the site with the hydrogen that's being abstracted. YRAD out, which is the radical that's abstracting the hydrogen. And then RNH, which is the backbone that links those 2 end groups. As you can see here, with a lot of these backbone ones, you'll have a lot of these other labels that don't participate in the reaction, but are important for determining the size of the ring transition state formed. And then you'll see other cases with a hydrogen. This is the hydrogen group. The star 3 label is associated with the hydrogen. The star 2 is associated with the atom that's bonded to the hydrogen. And star 1, which we'll see here, is associated with the radical. So in order to put data in here, we have, of course, a set of training reactions here. Some reaction label mapping a reactant to a product, degeneracy value, and kinetics information. Although a lot of the comments aren't quite as detailed as this particular case, but comments that describe where it came from, rank telling you roughly how accurate it is, and descriptions telling you where you got these calculations for a lot of these. But more particularly is that these reactions are stored with the labels on them. And this is very important because it lets you figure out where they go in the tree. And so you'll see that these reactants all have the associated labels. Okay. So if you're looking on the RMG website, you might see group additivity for kinetics. So when it was created originally, GAV-based kinetics was found to be significantly less accurate than rate trees. And so it's no longer maintained, although it can provide alternative estimates, but they're very, very mixed bag. So sort of the future and the direction we're going in terms of kinetics estimation right now is to use a subgraph isomorphic decision tree estimator, which is essentially, in some sense, is a software for generating optimized rate trees. And we're in the process of integrating this into all of the trees, but currently it's implemented for R recombination and retroene. These new trees are automatically generated rather than built manually, and are significantly more accurate than the original method, as you can see here. These generally operate on the principle that you have some general you take the most general template for the rate tree, and you put all of the training reactions at that node because they all match the most general template, of course. And then essentially you just pick each iteration. You pick any node in the tree that has training reactions that are splittable. You generate a possible set of extensions to the tree, new groups that could go below a certain group, and then we choose the best one that best improves accuracy. We extend the tree, we descend the training reactions down, and we cycle this through until we finish. And that gives you a tree. What's of particular interest is that these trees are one-dimensional, although that is less of an accuracy thing, and it's more of the fact that when you're writing these trees manually, it's a lot easier to generate a whole lot of complicated groups by writing three trees than not, because of the combinatorics, because you have all of the pairings between all of the different trees. So thermal libraries are relatively simple, and right now we're going to go through sort of the other aspects that we've sort of haven't touched on. They're essentially just sort of species mapped to thermo entries. And reaction libraries are similarly reactions mapped to kinetics, although this is a little bit more complicated because these reactions aren't associated with an RMG reaction family. And how RMG will treat these is it will assume essentially that whatever reaction you gave it is representative of how all of the cases where that reaction can happen and what ways it would happen. And so it will replace any exact duplicate reactions that RMG produces. What you should note is that it will not replace equivalent reaction paths. If RMG treats a sequence as A to B to C, and you give RMG a library reaction that simply just skips B and goes straight from A to C, it will not replace that equivalent pathway. It will think it's a completely different reaction. So let's take a little quick look at the thermo and reaction libraries. So here's an example of a thermo library. This is CBS-QB3 1D hindered rotor. And broadly, it has a description up here telling you where the data came from. And then each entry is essentially a molecular structure and adjacency list format, and then some thermo data that tells it how to calculate the thermochemistry. And all of these are pretty much broadly that. The reaction library is kind of similar to the training reaction set, except you don't have to have labels, of course. And so essentially you have entries with associated kinetics and an associated label and a description of where it came from. And then in the library, you just have unlabeled species identities. Okay. So to sort of talk a little bit about this, so we've gone through a lot of the stuff about the nitty gritty about how all of this stuff happens, but sort of the big important part of all of this is sort of this question of, well, I ran RMG and it gave me these values, and are these values accurate? So first, you should use some of the we've talked about a lot of these things, and hopefully that knowledge is helpful in sort of thinking about how these things sort of work and any rules of thumb we've given you. But sort of more specific cases. So if you have information coming from libraries, you should look at what kinds of sources were used in that library. In particular, whether certain parameters are fitted or guessed. And fitted and guessed parameters tend to may not be representative, may not be good values to use in a different mechanism situation. And so in a lot of situations, what might, especially if a reaction mechanism has been fitted to a specific condition, it may not be suitable for use in another reaction mechanism for a different species under different conditions. For thermochemistry, you should look at how specific the nodes are that estimate atoms, and this information should be available to you in the output Chemkin file, the annotated Chemkin file. Take a look, is there data at the node, or is it referenced to another node that's referenced to another node? For kinetics, in the traditional rate trees, if the Euclidean distance in the comment, which it'll say in the reaction comment in the annotated Chemkin file, if it's greater than 0, that often means it's not a great estimate, but you can take a look, and occasionally it is a good estimate. So you can look at the training reaction being used. If it's averaged, it's almost always not a great estimate. And even if the Euclidean distance is 0, you should take a look at what the source of the training reaction being used for it. Is the training reaction it's using for it is it a good estimate of it? And also, does the training reaction look like your reaction? And the automatically generated trees have an uncertainty estimation system, and that should be in the comments that you should be able to look at for that. But broadly, I hope this was helpful. Thank you for your time.